next experiment, that is common source amplifier. This is the second experiment which we are going to do. So first I will show you the schematic. So based on this schematic, we are going to draw the layout. So I will just explain in brief to understand this common source amplifier. So as I said, amplifier means it will amplify the weaker signals. So here Vn is the input, V bias is the biasing voltage, and we are using two components here. One is PMOS and one is NMOS. The PMOS and NMOS which we are used here are 4-port terminals. So it has 4 ports. So here if I concentrate on PMOS, the gate terminal is connected to the input, the drain terminal is connected to the supply, and the source terminal is connected to the output. So therefore, and the fourth terminal we call it as a substrate or bulk terminal, that is also connected to the supply. So because of this, now PMOS is able to provide a strong logic 1, or it will be able to pass the strong logic 1, okay, from drain to source. So here the input voltage which we have choose for this PMOS is a sinusoidal waveform or AC signal. And the next is V bias. The gate of the NMOS is connected to the V bias. We call it as a biasing voltage for NMOS transistor. So this is also 4 terminal. In that, this drain terminal is connected to the output, source is connected to the supply, and again here the 4th terminal also connected to the supply. This is because here the NMOS is able to pass a strong logic 0. Because of that, the bulk or the substrate terminal is connected to the VSS. So now the role of V bias is, so it will keep biasing this NMOS transistor based on the selection of input. So if the input voltage is 0, then the PMOS will be off. So at that time, so here the supply which is connected to the VDD that flows to the output side. So at that time, this NMOS will prevent the further voltage flows towards the ground. So when input is at high, means we are choosing the input voltage between the range which I will show you here. So this is a spice code here. The first is for the link or for the providing the connection to the tool. The second is the supply. We are defining supply from 0 to 2.5 volt. So maximum amplification possible here is 2.5. Then the ground, we are taking a ground with negative potential, that is minus 2.5. V bias again ranges from 0 to 2.5. Then the input voltage is Vin, ranges from 0 to 1, that is the time period for one cycle, which is of type AC. In that we are choosing sinusoidal waveform. Here 0 indicates the start of the voltage. 5 millivolts is the maximum peak voltage, means we are choosing Vn with the voltage of 5 millivolts. So 1K is the frequency of this sinusoidal waveform. First 0 indicates propagation delay, next 0 indicates this is a phase shift, and last 0 indicates the offset voltage. Here the offset voltage of this waveform is 0. So here first we perform transient analysis, which ranges from 0 to 10 milliseconds. Then we will perform the DC analysis, ranges from minus 2.5 to 2.5 at the x-axis, that is the voltage, and 1 millisecond is the time. Then for AC analysis, we choose the EC, that is decimal, or we can say that decibel dB, that is decibels. So the maximum frequency we are using up to 1 gigahertz or 1000 megahertz with the step increase of 100. So we will perform all these 3 analyses: transient, DC and AC analysis. So that also I will show you in the waveform. So first we will draw the schematic. So this is a schematic here. So V bias ranges from 0 to 2.5, keeps this NMOS on. When the input voltage applied is 0, PMOS will be on. The maximum supply voltage flows towards the output. When the input is at 5 millivolts, at that time PMOS will be off because it gets positive potential, and because of this here the whatever the this will become off, and whatever the output, that will flows towards the ground. So because of this, here we will get the amplification of input, okay, which is at 5 millivolts. We will get the output which is around 2 to 2.5 volts. Okay, so we bias to keep biasing the NMOS transistor with respect to the input voltage. So this is for common source amplifier. The main intention here is to amplify the input signal with common source. Source is common between the input and output. Similarly, the third experiment is common drain amplifier here. When I come to the common drain, so here the PMOS is replaced by NMOS, because the NMOS has the same phase shift with respect to input. So if the input starts from 0, the output also starts from the same phase shift, that is 0 also. And here, because of NMOS, the fourth terminal is directly connected to the VSS. Only that is the change here, and the phase shift here is between the input and output is 0 degree. When I comes to the common source, there will be a 180 degree phase shift between the input and output. The remaining stuff is same here in common drain. So we call drain is common between the input and output. So here this becomes the source, this becomes the drain now. They are interchangeable, and we are measuring the output at the drain. So the spice code also same here. So common drain is also called as voltage follower with amplified output. So voltage follower is nothing but whatever the phase shift at the input, the same phase shift is followed at the output. Okay, so this is about common drain and common source amplifier with respect to schematic. So I am going to draw these schematics. Based on that, I am going to draw the layouts also. Then we will verify DC, AC and transient analysis. Similarly for common drain. And the spice code for common source and common drain will be the same thing. Okay, so first thing, the only change in common drain here, that we are choosing, or we are replacing PMOS by NMOS, so that the phase shift between the input and output is same. When I come to the common source, the phase shift between the input and output is 180. So okay, so now in the next video I will show you how to draw the schematic and layout for common source and common drain amplifier. Thank you.